we will take a look at something really interesting, which is the trade-off between supply voltage and power on the one hand and supply voltage and throughput on the other. So the aim of this video and the next video is to look at methods to reduce power consumption in a CMOS circuit. Power consumption is really important because most CMOS circuits are now used in mobile platforms, and they are battery powered, and the amount of energy they consume is commensurate with the number of times that someone has to recharge their battery. But first we have to define what we are talking about exactly, because saying we talk about power is a little bit misleading. Imagine that you have a circuit, let's say that it is an adder, for example, and this adder works at a power dissipation level of P and is producing output at a throughput of S. Now imagine that somebody else says that they produced a circuit which is lower power than ours, and so its power dissipation is P over 2. This is not enough information because we also have to know what kind of throughput they are using. Because if their throughput is half, then they have actually done nothing to improve the design. Why is that? Because we could simply be using two of the circuits that they are using in parallel to produce double the throughput at double the power, which means that we have not actually made a low power design. They have not made a low power design. They have just cut the design in half. And so when we talk about power, we should compare powers for the same throughput, or otherwise compare the product of power and the inverse of throughput, which is power delay product. So the inverse of throughput is the time it takes to produce a single output sample. When we multiply that by power, we get the amount of energy required to produce one output sample, and this is the best measure of power we have. Now, if we look at dynamic power or active power, P dynamic was equal to alpha C F VDD square. We have several different options to reduce power dissipation, but the best option is to reduce supply voltage VDD. The reason is power dependency on supply voltage is quadratic, and so we get more bang for our buck from doing this. But we also have to notice that the operating frequency, which is inversely proportional to the propagation delay in the critical path, is directly proportional to VDD as well. So reducing your supply voltage will also reduce your operating frequency, which would decrease your throughput. So you have to think about it carefully. Now consider a circuit that is producing outputs at a throughput of S when it's operating at a frequency of F and a power supply level of VDD. In this case, it is consuming power at a level P. Now assume we use two of this circuit in parallel with each other and combine their outputs together. We are getting double the throughput, 2S, at the same frequency, using the same supply, and consuming double the power because each of these two networks is going to consume P. Now assume for the parallel circuit here that we don't actually want a throughput of 2S. We just want to preserve the original throughput of S. Right? That's all we need. We need an output of S samples per second. That means that we can operate these two parallel circuits at half the frequency, F over 2. If F is going to give us 2S, then F over 2 is going to give us S. But F is directly proportional to the power supply. So we can actually reduce the power supply by half and still get the same throughput. So what happened to power here? Power was originally 2P, so what happened to it? Right? We have to look at that. So power for one of the blocks was equal to CF VDD square. So power for the two blocks was 2CF VDD square. Now we have reduced the operating frequency by half, so 2C times F over 2, and we have also reduced the operating supply voltage by half, so VDD over 2 all square. And so then we get CF VDD square over 4. And so power is actually now P over 4. So we have managed to reduce the power by a factor of 4, and the cost that we pay is area. We are using two parallel circuits to produce the same throughput, so we are paying more area, but we are getting much less power, which is Kind of counterintuitive because more area means more capacitance to switch, which should mean more power. But the fact that you managed to reduce frequency had a more profound effect on power dissipation because it had a profound effect through supply voltage. Now, is the price that we are paying only in area? Because if that's the case, why not use 4 of these and reduce power by a factor of 16? Why not use 6 of these and reduce power by a factor of 36? There has to be a fundamental limit upon how much parallelism we can use, the degree to which we can parallelize our circuit. Of course, area, the cost of area is one aspect, but there's another aspect. Notice that as the power supply drops, the main thing that helped us reduce power here is that the supply dropped. If we use 3 blocks in parallel, we reduce the supply by a third, 4 by a fourth, and so on. And notice that as we reduce the supply, we also reduce the available noise margins. So that's our fundamental limit. Like if we keep reducing the supply, noise is not being reduced with us, and so we will hit a limit when our noise margins are no longer effective. There's a similar approach towards power minimization by using pipelining. Assume that you have a pipeline of logic blocks, right? So you have 3 logic blocks, CLB 1, 2, and 3. And they are originally or initially only I/O pipeline, so there's only pipeline registers on the input and the output. Now, this pipeline operates at a frequency F, producing a throughput of S, operating from a supply VDD, and consuming a power P, which is equal to CF VDD square times alpha, of course. Now, what is C in this case? C is the total amount of switched capacitance at the outputs of each of the logic blocks. It is the total capacitance that is being switched on average in this pipeline. Now assume that we perform pipelining on this network, so we perform internal pipelining, and also assume that each of these blocks have equal delay. So this is the best case for pipelining, right? When we have equal delay, because it reduces our critical path by the maximum amount. So now if we assume that in the original pipeline we had a critical path delay of t, we now have a critical path delay of t over 3, which means that the operating frequency has more or less tripled. It should be a little bit less than triple because we have the overhead of setup time and TCQ. But ignoring setup time and TCQ, it should have tripled by now, which means that the throughput has also tripled using the same supply. And the amount of power dissipation is now going to be a little bit different because we are operating at a different frequency. So power is going to be C plus delta, and this delta is the additional capacitance that we are switching because of the internal pipelining registers that we added, times 3F times VDD square. Now we're going to ignore this delta for now, it's not a big deal, and let's just assume that we are not interested in operating this circuit at 3S. We just want the original throughput of S out of the circuit. That means that we can reduce the operating frequency down to F from 3F, which means we can reduce the power supply from VDD to VDD over 3. If we check out the value of power dissipation, it's going to be P equals C times F, because we reduced our operating frequency down to F, times VDD over 3 all square, which means that power dissipation has reduced by a factor of 9, or 1 over 3 square. So we're basically seeing the same kind of improvement, the same quadratic improvement that we saw from parallelism, but we are seeing it with actually less cost because we are not multiplying the area. The area has not been doubled or tripled in this case. We just have the area of the additional pipeline registers, which is much less significant than parallelizing the combinational logic blocks. But we have the same limitations that we had in parallelism. We have to be careful about how much we reduce the supply voltage because noise margins are going to be reduced along with the supply voltage. With pipelines, we also have an additional cost, which is the cost in latency, the number of cycles that go until we see the first output. Latency is not usually a huge issue, especially when you have a latency of a few cycles, but in a large system where the latencies of multiple blocks can add up, this could have an impact, especially on real-time applications like video chatting, for example. So you also have to be careful with the cost in latency.